I want to talk first about a couple concepts we do when we're doing simulations. We want to try to make simulations as fast as possible. Especially in the loop where we're calculating energies or forces. And the reason for that is you have to loop around all the particles and all their neighbors. That's what 80 to 90% of all your computational time is in a simulation. So anything we can do to reduce the time needed to loop through all of those particles and calculate the energies and forces, it helps us out and makes it so we can get simulations done faster. Well, one of the tricks that you see in all simulation codes, it doesn't matter if you look at, simple codes like I've got or more advanced codes that you can get on the internet, is called a cutoff. You specify a cutoff distance for these non-bonded Leonard-Jones type particles. And the reason this works is if I draw the Leonard-Jones potential up here between two particles, you'll notice that eventually it goes to 0 at long distances. And so what I do is I select some sort of cutoff that's kind of close to where it goes to 0, where after that, if U is 0 after that, I don't need to add a 0 to a number to get an energy, right? So if particle 1 and particle 2, I might get this energy here, and I want to add that to my energy of my system. But if particle 1 with particle 3 is out here, I don't want to add that, right? I can save myself all the calculations to get like R6, R12, put them all together to get the force. I can save myself all those calculations if I just don't do them, if it's going to just add 0. So what I do is I select some distance, a cutoff distance, that after which I don't do all those other calculations. I still have to calculate R or R squared, because I can compare R to the cutoff or R squared to the R squared of the cutoff. But after that, I don't need to do all the stuff like R6, R12, do the U and add it to all the things. And then if I'm doing forces, I don't have to do the force calculation either. So cutoff distance. And on a Leonard-Jones system, it goes to 0 pretty close around 2.5 sigma. That's kind of the minimum standard. Less than that, you're probably going to get too many errors. If you're really worried about cutoff, then you go to 3.0 sigma. Right, where sigma is, about the width of the molecule. But after about 2.5 to 3 sigma, it's sufficiently close to 0 that I can just neglect it. So remember, U is equal to 4 epsilon sigma over R to the 12th minus sigma over R to the 6th. So if I ever calculate an R that is, say, 10 sigma, and I stick that 10 sigma into here, it's going to be so close to 0 that I don't care about it. And actually, if it's anywhere close to about 2.5 to 3 sigma. 2.5 gives us a little more error, but people do it because it's computationally fast. They don't do anything much less than that. 3 sigma is something if you want to really kind of be safe. In terms of angstrom, because remember what we usually do is we make this dimensionless. So I divide by epsilon, and I can get something like U star or U plus is equal to 4 R plus to the minus 12 minus R plus to the minus 6, because sigma over R is dimensionless. That's we dimensionalize with sigma. So if we ever calculate a dimensionless distance that is, say, greater than 2.5, then we just say U plus is equal to 0 for that pair. That's what we mean by cutoff. Does that make sense? Any questions on that? And this is something I specify in almost every code I know. We don't do it in necessarily the code in Excel. Well, what we do is we specify half the box length is our cut, but because that's what minimum image does by default. But in most codes, you usually set it to 2.5 or 3 sigma. In real units, if I was doing like a protein, I might do it like about 10 angstrom. After about 10 angstrom, two particles don't feel each other much from Leonard-Jones interactions, non-bonded interactions. If I was really being conservative, I could up that to maybe like 12 angstrom. I've never seen really any production of complex systems greater than 12 angstrom for proteins or for any other complex, lipids, polymers, things like that. But this allows me to speed up my calculations tremendously. Okay. I want to go down to chapter 8. There is a concept that we want to talk about. It's called the radial distribution function. I don't know where it's written now, maybe on this page back here. We do it with RDF, or we make the acronym RDF, but it's called the radial distribution function. Now, any of the graduate students, you might remember this from last week. Does anyone remember that from last week's seminar speaker? He happened to talk about radial distribution functions. Are you graduate students alive out there? Is anyone alive out there? I know Nathan prayed, but no one else seems to want to talk today.
Yeah, we're alive.
Okay, the other Nathan's alive.
Yep, it's just the Nathans though.
So Joy or Tyler, Jared, Tyler Free, Jared, did you guys remember what the speaker spoke about last week? He talked about radial distribution functions. And what a radial distribution function is, it tells me something about the structure of the fluid. And it's something I can actually get experimentally. I can get that by like neutron scattering. If I take neutrons, bombard a sample, I can see how they scatter. And then I can back out kind of a structure. We don't think of liquids as having structure or fluids having structure, but they do have structure. What we mean by that is this. If I look at, say, a central particle, or a particle, I can kind of consider that the center of my universe for a minute. And then I can look at every other particle and look at how far away it is. And you can kind of see about, 1 molecular diameter away, 1 sigma, or 1 in dimensionless numbers, I kind of have a shell of atoms. And then if I kind of look 2 molecular diameters away, I have another shell of atoms. And I can quantify this. If I start just keeping track of how many particles are in each shell a certain distance away from me, so I can do it at, say, a dimensionless distance of 1, 1.02, 1.04, 1.06, 1.08, or what, I guess these are 0.1, so 1.1, 1.2, 1.3, 1.4, 1.5. I can count how many atoms there are in that shell. And what I really do probably, right, is I bin it. So I say between 1 and 1.1, I count how many atoms are there. And so I can get a little local density because I also know how wide that shell is, right? How much volume that shell would be in a spherical system. And so I can get N, I can divide it by the volume of that shell. And I can get a local density. And I can do this for all the particles in the system, right? I can consider every particle, look at all its neighbors, and I can get a lot of averages about how far away on average the particles are. How likely it is that a particle is 1 molecular diameter away, 1.1 molecular diameters away, 1.2 molecular diameters away. Then I can normalize this. I can say, I know what the bulk density is. The bulk density is all my particles over the total volume. And I'm going to define the radial distribution function g of r as rho at that r, so the local density normalized by what the bulk would be. And if I define it like this, what this tells me is how likely it is that a particle is a certain distance away compared to the bulk. So eventually, as I look far enough away from my particle, this radial distribution function becomes 1 because my local density will equal my bulk density. But you'll kind of see in this first shell especially, and maybe even the second shell, there's a very high likelihood that particles are about 1 molecular diameter away. And that's why this goes so high up, right around 1. It's more likely for a particle to be 1 molecular diameter away than it is to be 1.5 molecular diameters away. And then I get another shell about 2 molecular diameters away. And so here, it's more likely or more probable to have an atom that distance away, that's my first shell. And then here, I am less likely. Nathan, what's your question?
Yeah, so this bulk density, is that like closely related at all to like the macroscopic density that we would like measure or observe?
Yes, and so definitely. So what I can do is, in simulation, I'm not dealing with Avogadro's number of particles, but I say have 500 particles, and then I can divide it by the volume of whatever I've got, you know, like 100 angstrom cubed or something like that. And then if I wanted to, I could multiply that by Avogadro's number, or multiply by Avogadro's number to get what a density would be in real life. Or I could multiply, I could do it on per mole, or I could do it per mass, or whatever.
I guess like the implications of that would be like, could we use this with like, for example, a density that we like measure in like a macroscopic scale to fit our data?
Yes, you can. In fact, that is what, that's what we do when we parameterize a lot. If I want to, it's commonly done when I'm doing hydrocarbons and I'm looking at phase equilibrium. Phase equilibrium is a huge thing, right? You guys are taking separations, or you have taken separations. It's one of the keys of actually getting usable product, right? I got to purify. And so vapor liquid equilibrium is a huge field where there's lots of simulation work. And often what they do is they parameterize their model. They pick the densities in the liquid and vapor phases where you have equilibrium. And then they want to make sure that they make the sigma and epsilon replicate that. So that's one way that people do it, is they look at the macroscopic densities and make their simulations give them that. So that's kind of the macroscopic. When you look at the macroscopic properties and you build from the top down into your model. The other way you can do that is build from the bottom up, similar to what our graduate speaker talked about last week that I was mentioning. I can do neutron scattering and it will give me radial distribution functions like this. And then so that's kind of the microscopic level. And I go from a bottom-up approach to make sure my parameters give me this. And so yes, radial distribution functions are actually quite amazing because they contain so much information about the system. I can relate them to something that is macroscopic, or I can get experimentally. While I'm kind of thinking about this, if I looked at the radial distribution function of a solid, what would it look like?
It would probably have like a bunch of consistent waves until you got to a really far distance where it would again drop to 0.
So yeah, so you're very close. So it's not even going to be waves now. It's going to be more like delta functions, right? Because those atoms are kind of stuck in the lattice. As long as I have like a nice crystal, if I looked at a perfect crystal, what I'm going to have is a bunch of delta functions where on my crystal lattice sites, it's kind of a very high likelihood, right? It's going to be there, but it's not in the interstitial region, so to speak. It's not between the lattice sites unless I had some sort of dislocation or something like that. So for a solid, my radial distribution function limits out to like a bunch of delta functions where they're separated out by the lattice space of the lattice constant of whatever sample you have. So if you kind of think back to all the way back to materials class, you guys talked about, how far away atoms are in crystals, crystal lattices, BCC, FCC, all that sort of stuff, then that's what it would look like. The radial distribution function will look like a bunch of delta functions. And then if I go to a gas where I'm less dense, I don't see quite as prominent peaks, especially after the first peak. It levels out to 1 much faster than maybe a dense liquid. Now, the great thing about these radial distribution functions, aside from them being so relatable to experimental things, is that they contain so much information of the system that they can actually be related to properties. And if you go down in this chapter, if I have the radial distribution function, I can actually calculate the internal energy of the system without ever doing a simulation. So if I got that neutron scattering data, I could do this integral. So here's my G of R, and it's a little complex, right? You'd have to do this numerically, but that's okay. You have a G of R. Remember, the G of R looks something like this as a function of R. R squared, that's self-explanatory. I could stick in whatever parapotential model I care about, usually Leonard-Jones in this case, and do this integral. And it converges fairly quickly, so I don't necessarily have to go out to infinity, but I can get the potential energy of the system. The C just kind of reminds us that it's from the configurations, but the potential energy is always from the configurations. So the potential energy of the system from this G of R. I can also get, if I skip down and then I'll come back to these corrections, I can get the pressure or the compressibility factor, and again relate it to macroscopic properties. I have to take a derivative of my potential here, but that's not hard. We know how to take derivatives of r to the 12th and r to the 6th, or r to the minus 12 and r to the minus 6. But I can get pressure, and this is fantastic, right? Because it allows us to get a macroscopic property if we know these microscopic systems. And those are kind of the two big properties, I guess. If you know the radial distribution function, you can get the energy or you can get the pressure by this integral. And don't get confused again by the R stars. Remember, the R stars are just means we're in dimensionless numbers. We've divided the energies by epsilon. We've divided all the distances by sigma. Okay, so any questions on radial distribution function or these equations right here? Because we use these to get some long-range corrections I'm going to talk about. We're going to combine these concepts of cutoff factors with radial distribution functions. Okay. The radial distribution function, remember, it goes to 1 at long distances. It starts at 0 if I'm overlapping too much, because there's the likelihood that a particle is going to overlap totally is very small. But for a soft thing like Leonard-Jones, it starts overlapping a little bit right around 0.8 sigma. So that by the time it gets to 1 sigma, it's high likelihood. And then 1.5, it comes down. Might have a second shell, might even have third shells or fourth shells, but eventually this thing gets out to 1. And then, so this is about 1 sigma or dimensionless 1. This is about 1.5, and this is about 2. Well, we know that eventually it goes to 0 or it goes to 1. And so I'm going to combine this idea with my cutoff potential. It often goes to 1 about where you are cutting off your Leonard-Jones potential, which kind of makes sense. So if I'm cutting off at 2.5 sigma, then my radial distribution function is going to go to 1 about 2.5 sigma because nothing fills each other. They don't fill each other after that. Or it might be 3 sigma or something like that. But the point is some point down here after my cutoff, I'm assuming the interaction's 0. I'm going to assume, say at 2.5 or 3 sigma, let's do 3, that my G of R is equal to 1. So every time my potential is equal to 0, I'm going to assume my G of R equal to 1 because that allows me to split up this integral and calculate a correction for any of the interactions I might be missing because I did a cutoff. We know, right, it's not strictly 0, the interaction. And so I can get a little bit of a correction. Or G of R is not equal to 1 below my cutoff, but above my cutoff, I'm going to say it's equal to 1. And I split this integral up, go between 0 and my R cut. That's what RC means here, R cut. 2.5 or 3 sigma, 2.5 or 3 dimensionless. And then I go from the cutoff to infinity where I assume the G of R is equal to 1 because I can do this integral if G of R is equal to 1. And so we call this second part, this integral from RC to infinity, where we assume G is equal to 1. We call this our long-range correction. And it's a constant. It's a constant because I know that G of R goes to 1. And so you can see the math there, but this is what it comes out to be. And so I can calculate that at the beginning of the simulation, and I know what the correction is to the energy. So I'm going to do all my pair potentials. I'm going to cut off at 2.5 sigma. And so that induces a little error, but then I can actually correct for that error because I know that G of R is equal to 1 after that. So I've saved myself time, but I still have fairly good accuracy with my long-term cutoff, my long-range cutoff. And I can do the same thing for pressure. I'm going to cut, because I'm still cutting off my interactions, I can correct for pressure similarly. And so this is just the equation for Z. I'm going to split that up into, sorry. I don't know why it always zooms in sometimes. Sorry, actually, this is Z correction. This 0 right here should be an R cut on that lower bound. I'm going to assume this equals 1. And so that when I do my integral, I can calculate the long range correction to pressure. It's just one value based on whatever my cutoff is, and correct for my pressure or my compressibility factor. And so in the codes that you will see, almost always you'll see long range correction, or LRC, written. And I'll show you that kind of when we do our codes here in a minute. So there's 2 big concepts we talked about before we get to codes. Cutoffs that I do because after some cutoff, it's close enough to 0 that I don't want to bother with the math. I want to save myself those computational iterations and just call it 0. And then radial distribution function tells me something about the local structure of the fluid. And because I know that information, I can relate that to physical properties. We don't go through all the derivations there. You can look at a statistical mechanics book, but I don't think you necessarily need to know how to do that, or you don't need to know the proof to kind of understand how to use them. Any questions so far on those 2 concepts? Okay. I want to return, how do we calculate the radial distribution function? What we do is basically we need to create a histogram or count the number of particles. I thought, where is that? Oh, right here. We have to count the number of particles in each shell. So I have to somehow create some bins. I want to maybe bin up between 1 and 1.1 in R, 1.1 and 1.2 in R, 1.1 and 1.3 in R, or 1.2 and 1.3, or I could go by halves. That's something I have to select. How many bins do I want to do? The more bins I have, the longer I need to simulate to make sure I fill all the bins, right? The smaller I make my bins, then I've got to make sure the particles have a long time to fill all those bins and get a good average. How do I get the bins? How do I tell, or how do I calculate these bins? Well, here's one way to do it. To calculate the histogram for that RDF, right? We're going to calculate how probable it is a particle is, 0.8 away, 0.9 away, 0.10 away, or 0.10 away, 1 away, 2 away, 3 away. Well, before I forget, there's
something you calculate every time step, every few time steps, or do you just kind of stop at the end of your simulation and calculate it all one time?
You don't want to do it just the last because you won't get good averaging, but I have my code set that you can tell it how many iterations, how often you want to do it. So I usually do it maybe like every 100 steps. You don't want to do it too often because then it starts to become a computational hindrance, right? It does cost a lot of energy because I have to loop over all the particles and calculate the distances. And so I might only do it one every 100 cycles or one every 200 cycles. And I'll show you that kind of in a second. Before I forget though, this code has an error as it's written. This 0.5 should be a 1. And I'll go through the math of why that is in just a second, but just make sure you kind of know that that 0.5 is actually a 1. So to calculate a radial distribution function, remember what I'm trying to do is I have to calculate if a particle is in a shell, a spherical shell, at every distance. And the distance that this code uses in the Excel sheet that you have uses a bin width of 0.03. That's just the way Dr. Rowley coded it. Nothing too special about that. I could go smaller, I could go bigger. If I go bigger, right, it just means I don't get quite as smooth. If I go smaller, it means I have to simulate longer. So that's my bin width. This number is where I'm going to start my bins. The particles are never going to be less than, say, 0.8 is what we're saying. And so I don't need to bin all the way from 0. I could bin from 0. There's nothing special about this. It just saves me a little memory to start at 0.8. You can select this in the code that I give you. If you wanted to change it to go to 0, you could make that a 0. But this is the starting point of my histogram. And again, this is just one way you could code this. So what I do is I loop through all the particles, particle 1 to n-1, particle plus 1 to n. Actually, let's talk about this to make sure we kind of understand this. Does everyone see that if I go from, this is like my I and this is my j. If I go I equals 1 to n-1, and then j equals I plus 1 to n, why do I always construct my double loops to do this? Why doesn't it go 1 to n and 1 to n?
Going 1 to n on both would double count each time.
That's right.
It would make 1, 2, and 2, 1 identical, I guess.
They are identical, but I would be adding it twice, right? And I don't want to add it twice because it's a pair potential, right? 1 and 2 give me one interaction. One pair gives me one interaction. And so yes, this is, you want to just make sure this not only speeds us up, but it correctly counts things, right? And so I'm going from 1 to n-1 because that last pair is between, say, particle 499 and 500. I don't need to go 500 and 500 or 500 and 501 or something like that if my n is 500. So yes, so that's, just make sure you kind of see that that is common in the loops that we go around, these double loops. But I go through, I calculate, dx, dy, or delta x, delta y, delta z. I do minimum image. Remember what minimum image is because I'm doing a periodic image. If I ever calculate a distance that is greater than half the box length away, that means I have another particle in my image that's closer. And it's one length away, or one cube. Remember, cube is the length of the box. So I get my dx, dy, dz with minimum image, calculate the distance, just normal square root of delta x squared plus delta y squared plus delta z squared, right? Similar to what you learned back in algebra of how to calculate the distance between points. Probably only did 2D, but now we're in 3D. This line, you really don't need. It just is cutting off the graphing. I have something called plot max, which I think in the code is something like 3 or 4 or something like that. It's just for graphing. We just didn't want it to go infinity, or Dr. really didn't want to get a memory overflow. I don't have that in my code. It just, if it's outside the bounds, it just ignores it. It doesn't add the histogram. And then what does this int function do? So let me draw this out for you for a second. I've got an example here that I've got. So let me look. So I'm going to set this up 0.8. We're starting at 0.8. This is one bin. And then we have our next bin at 0.83. Remember, we're doing bin widths of 0.03. And then we have the next bin at 0.86. So those are how my bins are set up in this code. Bin widths of 0.03, I start at 0.8. And then I could go on and on and on and on. And so my first bin is between 0.8 and 0.83. My second bin is between 0.83 and 0.86. Let's say I have an R. I calculate the distance between 2 points as 0.84. That's going to put me, technically right here. I want to be in bin 2. Does that make sense? I want to count that particle as bin 2. And so let's look at how this bin statement works. It does int of zero. So it's, let me go back up. Distance minus 0.08. So the distance is 0.084 minus 0.8 over my bin width, 0.03. And so this gives me 0.04 divided by 0.03. Oh, sorry, I have to add the 1 in. And I have to take the int of that. 0.04 divided by 0.03 is 1.333 plus 1. I take the int of that. It's the int of 2.333. And when you take the int, it just cuts off the decimal. So I'm in bin 2. This is just a way to figure out which bin I'm in. Does that make sense? Any questions on this little? So what I did is just gave you an example of this statement right here, how that works. And you can see why it has to be 1. No, don't forget this correction here. I made it, I'm going to change colors there. I made it, it has to be 1 or it wouldn't work. And I can't remember if I changed that in your code or not. I mean, you're only off a little bit. Our bin widths are so small that it's probably not a huge deal for illustration purposes, but it should be 1 to be strictly correct.
Quick question.
Yes.
Does int round to the nearest integer in
Nope.
Excel or cut off?
It just cuts it off.
So if it did round, would we want to do that
If it
that
rounded,
0.5 instead?
Maybe that's why it thought, maybe if he thought it rounded, it would be 0.05.
Okay.
But
Sweet, thank you.
The round function is usually what you use in Excel to get it to round. Int, I'm pretty sure just cuts off the decimal. And I know in C or Python or whatever your other favorite language is, when you do int, it just cuts off the decimals.
All right, thanks.
Okay. And so then I just keep track of all my bins. I have this array called num. And I keep track of all the n. And then you can kind of see if I just know all the n, then I can use that here. This gives me my n in that shell. I can calculate the volume of that shell because I know the distance. It's I would probably, right, this is I can calculate the delta here and then do 4 pi r cubed, or 4 pi r squared times that 0.03. So I can get the volume of that shell. And then I can divide it by so that gives me my local density. I divide that by the bulk density to get my G of R. Now, you can actually use histogram binning packages like in Python or C to do this. That's what my code does. I just have a general histogram package that you tell it what your histogram is, what the bin widths are and how many there are, and then it will start accumulating the histograms like that. So this is just manually how you could do the bins, but you could use a histogram package in your favorite computer program. Okay. Let's now go and do some, I'm gonna go back to my other computer. So get open your shell that you see. Let me share my computer on this one now. If you already are familiar with Linux or you've done the supercomputer, this might be a little boring to you, but just bear with us so that everyone else. And if you want to chime in and give us some hints, then you can do that. But you should see something like this on your screen. I'm going to make mine a little bigger. Is that font big enough for you guys? Can you see that fairly well?
Yes.
Okay. Now, one of the challenges, if you've never used Linux, that I hope you kind of went through some of the basics of Linux. The first thing we want to do is log into the supercomputer. And the supercomputer, so SSH is a common command. It's called secure shell. That's how you log into other computers wherever you are. And if you went through the supercomputer tutorial, you probably saw this. But I want to SSH into the supercomputer, and they call that ssh.fsl.byu.edu. They just created this alias that's how you log in. That's the name of the supercomputer. And when you log in, you're actually logging into, one of several head nodes. Mine might be different than yours because they want to make sure they have enough bandwidth and everything. But they just made this go to the one supercomputer. When I hit enter, it's going to ask me for my password. And then the verification code. And I hope that you kind of got this figured out, but you have to download this on your Duo app. Right, it'll give you, mine looked like something like this. It gives you a one-time code. That's why I can show it to you. It changes every like 30 seconds. And then you log in. I don't know if mine's the same as yours or not. So you're going to have to authenticate, just double check with your own Duo. Anyone have a hard time logging into the supercomputer?
So I didn't this time, but when I was originally testing it on Monday, it takes about, I'm guessing about half an hour to an hour from when you create your authentication to the supercomputer actually accepting it.
Oh, but you're all in now. You've got all your Duo. Let's see, let me check chat. Okay. So I want to just give you a little idea. LS is listing all my folders or files that are in my home directory. So Linux has something called a home directory. Microsoft calls their home directory what? Documents. It used to be called My Documents. I don't know what Apple calls theirs or Mac, but it's called the home directory. That when you first log in, this is kind of your main place that you can make folders, make files, all that sort of stuff. And you can see all sorts of junk I got here. But I want to highlight a few things. FSL groups. So you want to go into FSL groups, CD. So that's change directory if you don't know. FSL groups. And if you know about Linux, you can hit tab and it will correct, or it will auto finish your folders or what you're typing. So if I go in there, you should all be members of this FSLG _ Chem Engineering 513. So you can go into that folder. And notice I've got just one thing in there for you guys, submit.sh. Just be aware that we've got this group folder that we can copy. I can copy stuff to you. You can get it. You can write to it, all sorts of stuff. We're not going to do anything necessarily right now. I'm going to hit CD. And when you hit CD, enter, it takes you back to your home directory. And so you can see that I'm back at home. Now, I have a folder called junk. That's just where I put stuff that I'm just kind of playing with. You can make a folder whatever you want, but the way you make a folder, mkdir. So make a directory or a folder and then give it some name, whatever you want. Temp, junk, practice, whatever. I'm going to go over to, or you don't even necessarily need to make one. I'm just going to put this in my junk. And you notice I got several codes in here that I'm playing with. I'm going to remove this Leonard Jones code because what I want you to type is this. So you remember my code is stored on GitHub, this Leonard Jones code. Let me bring that up right here. Remember, you've got this that you could download, but you don't have a GUI to download on the supercomputer. And so the way to do this command line is type git and then clone. You're going to make a copy or a clone of this directory. And then you're going to go https://. So we're going to get it from the web. And then it's github.com. ljmdmc.git. So type that in and you'll hit enter and that will download what is in that directory. And then when you look here, you'll have something called ljmdmc. That's the code from Git. So here's the command. Please doesn't kill me again. Type that, hit enter, and you should get ljmdmc. While you guys are making, anyone have a hard time with this?
Yeah, mine's asking for a username, a GitHub username.
Really? Is anyone else? Did you put the .git on the end?
Yeah.
I did that and it worked for me.
Maybe I typed it wrong. Try again.
Maybe Git is somehow already knows I've got a username. Do you have a username on GitHub?
Yeah, I could try that.
Try that one.
I think usually to clone things, you need to have either the, like an account, or you have to enter in the SSL like secret and key in order to get to clone stuff without entering your passcode. But usually you have to enter.
Who else had a problem with this? Well, here's what I'm going to do for anyone that has a problem. I'm just going to copy this into our group folder, and then you can just copy it from there.
It worked for me this time when I tried it again.
Oh,
I don't
okay.
know if I did different, but.
Okay. Anyone else not get it? Because I can just stick it in the group folder. Okay. If you're wondering, these other codes I have in my junk folder, Spidey, the code. So when I was a graduate student, we were making a Leonard Jones code or a simulation code for proteins. And it's right when the first Spider-Man came out with Tobey Maguire. That's how old I am, right? We're like 3 generations into Spider-Man now. It's when Tobey Maguire Spider-Man came out and we didn't have a good name for it. So the colleague that was writing it with me just called it Spidey. And that's what, it just stuck forever. And then when I got to Utah here at BYU, I said, I'm just going to call it the code because I'm sick of calling it Spidey and I got to come up with a better name. And I never came up with a better name. So now it's just called like the code. And I changed it from capitals to lowercase just because I got sick of typing lower capital letters. So if anyone's got a good idea for a code name, then that's it. Then tell me so. Okay, I'm going to go into ljmdmc. So cd ljmdmc. And if I list ls, this directory, you see it's got a bunch of files in it. This is the code that's basically doing the Leonard Jones simulation. Okay. It also has some sample files. It's also got some documentation. So If you download that, there's a PDF that kind of explains how to run this. But what I'm going to show you is how to build this on the supercomputer. And building is compiling is the correct nomenclature. You compile this code. So if I kind of look at VI is VI editor, or sometimes you use Vim. If you just type VI, it gives you Vim. But you've got to learn some editor, some command line editor, and VI is kind of the standard one. I'm just going to look at main right now. Then you can kind of see that this is the code that it's going to run. This is the main subroutine. And if you don't know C, you're going to be looking at this and think, oh, that is a lot of stuff I don't get. Don't worry about that, because you're not going to have to really do a lot of coding here. If you want to do C, I can help you. If you want to do the Visual Basic, I can help you there.
What command did you type to look at that?
So VI is an editor. I can't remember what it's called. Visual, I don't know what it is. Visual Interactive. But VI is just an editor that's been around for decades, and it works command line. There's one called Emacs too, but I just use VI. I've always used VI. And then you give it the name of whatever file you want to view. You can look at any of these files. I'm just looking at the main one. So VI, then you'll be able to look. Now VI is an interesting editor. You're going to want to spend a little time kind of practicing, because there's two modes to it. There's a visual mode that you kind of default into, and then there's an editing mode. So I can't actually really like start typing. If I wanted to change something right here and I started typing, you know, ABC or whatever, it's going to do something weird. And that's because you're in an editing mode. So it has two modes. So if I wanted to start typing, I'd have to hit I, and notice down here it said insert. Now I'm in insert mode, and I can start kind of doing the normal thing. I can type, I can delete, I can move around with arrow keys, things like that. Old time computers didn't have arrow keys. And so that's one of the reasons they had VI. So if you hit escape, it goes out of insert mode and back into the editing mode, or the moving around mode, because you used to have to move around with your keyboard, like JKL or HJKL or something like that. And those still work, I think. Like J moves you down and K moves you up, and L moves you to the right, and H moves you to the left. But that's what historically VI is everything had to be done with just computer keys. There were no arrow keys, just letter keys. And so HJKL were the arrow keys. And then when I wanted, so I'd move around with those. And then when I got to where I wanted to, I could hit I to insert and then start typing or deleting or whatever. So I, and then escape to get out of insert mode. I to get into insert mode, escape to get out of insert mode. And then to get out of this, you have to hit escape, be in the not insert mode. I can't remember what it's called. You remember what it's called? The non-insert mode. Then I hit colon, so shift semicolon, and notice that I get this little thing down here, and I can hit Q to quit. If I wanted to save the file, I would do W for write. So W is to write, Q is just to quit. I don't want to save anything. It's going to say, oh, you changed something because I was messing around. I'm going to force it to quit. So if you put an exclamation part, I don't want to write anything I just changed. So if you need you can search online. There are all sorts of VI tutorial. You can search through there and get all of the basics on VI. Okay. If you're in LJMC, the thing I want you to do now is just type make and then hit enter. And you're going to see something that looks like this. What that's doing is compiling the code and giving you an executable. And the executable name is called LJMDMC. And you kind of see that right here. So anyone that knows a little about computer programming, what this is saying is GCC is the GNU C compiler. And so it's a free compiler. I told that, I'll tell you in a second how I told you that. -03 means these are some flags you can give the compiler to optimize it, to make it faster. And then I'm using the C99 standard. So that's what all that is. There's just some other things, but it goes through everything. So there's an allocate subroutine, there's a atomic potential energy, a finalized forces, and then it makes computer code for each one of those, and then it puts all the computer code together down at the bottom, and then gives you an executable. So now I have an executable called LJMDMC right here. Does everyone see that? Anyone have a hard time not making it? So make is a command on Linux. It's GNU make. It takes what's called a make file. It looks for something called make file. So right here is all the instructions I gave. You guys can see my cursor, right?
Yeah.
Make file, if I look at that, so VI make file, you never really need to change anything here. But this is telling the computer, I named it LJMC. So this is just, I'm naming it this. You could change this to your name. You could change it to junk. You could change it to Spidey. You could change it to whatever you want. It's just the name of the file that it's going to make for your executable. This tells me I'm using the GCC compiler. And these are the flags I gave the compiler. You really never need to mess with that. In fact, you don't need to mess with anything here unless you kind of wanted to change. But all this is just saying that take all of these files you see, make object files using the GCC compiler, then link them all together and give me an executable. So you really need to never change anything here. Just show you make looks for this file, and then it makes the executable using the GCC compiler. Now, I have this LJMDMC executable. I need two other things now to run this. Well, one other thing. So I'm going to, let's copy LJMDMC. And I want to put it into the folder called sample files, MC, right here. So do this command, copy LJMDMC, so that's your executable, into this folder called sample files where I have some input folders for you to use, input files for you to use. So copy LJMDMC to sample files MC. I've got examples here for MD and MC. We haven't talked about MD, but I'm putting it in the MC file. And so now I'm going to go into the sample files where I just copied this, and we're going to run a little quick simulation. So let me know if you didn't get it copied. Okay, let's go in CD, change directory. And then if I ls this, you'll see I've got a copy of my executable here. And then I've got a sample input, a sample output, and then also this weird looking named file. So let me explain what this, first of all, let's look at MC example.input. So if I look at that VI, if I open it, MC example input. You'll notice that I'm hitting tab to autocomplete, and you just kind of get used to that when you're looking for Linux, working with Linux. So I just typed MC, tabbed over, and it gave me some other options, and then I hit I, tab over. The VI MC example. And this is a fairly, it's typical of what you'll see in a modern computer code for doing simulations. You have a bunch of keywords. That's what's in the first column. And then you have the options for these keywords. And then you'll have this option to put comments in. These comments are not needed. They're just to help you, remind you what you've got in your code. It doesn't read anything after that. So I've got a bunch of keywords, and we're going to talk through each one of these. And then I got a bunch of the values that I set to my keywords. So sim, the code's going to look for what type of simulation you want to do. It can either be MC or MD. We're going to do MC today because that's what we talked about. N is the number of particles, 500. That's actually a pretty big number compared to what we've running. We were running like 49, 25, something like that, because we were doing it on a slower code with Excel. You can change that to something else. All right, this gives you the freedom. I have to set the temperature. This is the dimensionless temperature for my Leonard Jones system. You're right, this can be something very low, up to like 2 or 3. We're going to be above the critical temperature. You really don't know that in Leonard Jones, but It's not going to be like 10 million. It's not going to be, right, it's even more than 10. Usually we're in the, the 0.5 to 2 range, or maybe 3. Density. I get to select what density I want. And it's going to use this density, this dimensionless density, and my number of particles to calculate my box length. You don't give it the box length. You give it the number of particles in your simulation, and then you give it the density, and it will calculate the box length you need for that. And then here's telling me how many steps I want to do. So E steps is equilibration steps, and P steps is production steps. Remember, if I just start out with the simulation, I usually kind of just put the atoms on lattice sites, but that's not where they want to be. So I want to allow the system to move around before I start calculating averages. I call that equilibration. And so that's what E steps is. And then P steps is the number of steps I'll do when I start to calculate averages. I want to keep the data after that. What do you think this is compared to our discussion for today?
3 times the atomic diameter or something?
It's not in the, we're dimensionless. It is close to
That's how far out you're, like, instead of the 2.5, you're going to the 3. So you're being extra careful.
So this is my cutoff for Leonard Jones. I'm going to make everything 0 after 3 dimensionless. So about 3 sigma or 3 dimensionless. So if I wanted to, I could make that 2.5, or I could make it 3.0. I just had it at 3.0 for this one. The smaller I make it, a little more error, but I'm a little faster.
Dr. Knotts, what does it do if n isn't a perfect cube? Does it just leave some gaps?
Yes. So like when, you mean like if I, really this should be like 512 if I wanted a perfect cube or something like that, or I don't know what the cube root is, but it just leaves one row that's undone, which is okay because I am just going to equilibrate anyway. So I guess you could figure out, what is it? 5 times 5 times 5 would be 125. And so I don't know it's not 10, it's not 7. What's 7 times 7 times 7? Whatever that is, maybe that's going to get us close to there. But if it's not a perfect cube, then it will just leave some vacancies in my crystal. But again, that's just to initialize it. I don't necessarily care about that. This DT, I didn't know what to call it, DT or something else. It's the delta, the max delta in dimensionless units. We kind of talked about that yesterday. The max any displacement can go is 0.1. And it's going to change, update that 0.1 as it on the fly to give me an acceptance criteria of about 30%. Okay. So that's just where it starts. Coordinate, you can specify 2 different things. I can give it a file. That's what I've got, a file name. That's what I've done here. Or I could give it generate. If I give it generate, it will make an FCC lattice, kind of what we talked about. It'll just lay protein, or this is the initial coordinates. It will lay the atoms down in just a lattice structure. If I give it a file name, it's going to look for the file name there and then use that as its initial coordinates. And so I'm going to go out of here just real quick and look at this. I gave you this file right here. N means 500 particles. Temperature is 0.85. Density rho is 0.9. That's kind of my nomenclature. You can name it whatever you want. You don't have to use that nomenclature. And so I've already run a 500 particle system at this temperature and density. And if you look at this, it's just a list of 500 XYZ coordinates. And so there's 500, if you do set number, there's 500, that's the line numbers you see on the left. There's 500 XYZ coordinates, 500 particles, one set of coordinates for every particle. Again, this is just so I don't have to equilibrate as long. I've already got this from another simulation, and I can use that as a starting configuration for my simulation. Or I could say generate in my input file, and it will just lay it down on a FCC lattice. Output is every 50 iterations, it's going to write stuff to my file and to the screen. So I kind of know what my simulation is doing. I don't want to do this every iteration because then I'm outputting so much data, my files get huge. But 50 is probably okay, because if you think I'm going to do a total of 30,000 steps here, and if I'm outputting ever 50, so I can divide 30,000 by 50 and what, get like 6,000 or something like that. So 6,000 lines, that's not too bad. That's probably still a lot, but I could put that at 100. When I do MD, I probably want to make that even bigger, like 10,000 or 5,000 or something like that. And then the seed, this is an optional one. We kind of talked about this before. Random number generators need a seed value. And you have some options here. You can let the seed be generated from the system clock, or you can specify some random negative integer. The negative is kind of historical. All the old random number generators, always you had to give it a negative integer because then it would know that that's the initialization one. Newer libraries just put the negative on there for you, so you can just give it a positive, but I make you put a negative on there just because I coded from old school type things. But you can just put generate here if you want. Whoops. That will generate it from the system clock. Let's see, what was I? And then finally, this is an optional one. If I have radial distribution function in, it'll calculate the radial distribution function and output it at the end of the simulation. And you'll notice here, I give it the starting value for my bin. So I'm going to start at 0.8. I'm going to go out to 4. I'm going to use 100 bins across that. I don't know what that makes my bin width, but you could set that to 100, 120, whatever you do. And I'm only going to calculate it every 25 iterations. So you can select all of that. You don't want to make this every single iteration or it's taking too much time. 25 is kind of a decent number. So I want to make a couple changes for a second, because if I ran this right now, it would take about an hour and a half to complete. And we don't want to go that long. So I'm going to reduce this to about, say, I'm actually going to do it to say 10 steps and 20 steps. And because of that, I'm going to change the output to every 2. And so remember, the way to do that is you can go to insert and use your arrow keys and just hit delete and type and things like that. So make sure you're in insert mode. I wasn't using insert, I was using a fancier key. Sorry about that, but insert mode and change this to 10, this to 20, and then change this to 2 so we can see some output. And then the way to save this, you hit escape, you hit colon, and then you hit, what I would always hit is X. X means write and exit. Another way, some people do WQ, which means write and quit, but they have a one-letter one called X. I always hit X. So that means save that file and exit. So any questions up to this point? Everyone able to change their files? Okay. Here's how you run this simulation. And because we only gave it a couple iterations, I'm just going to run it on this machine. Normally what we'll do is we'll submit this job to the supercomputer. We'll probably have to talk about that next time, or you can figure it out on your own. There's lots of stuff online. But I am going to type LJMD, so /LJMDMC. That's the command I'm going to run. And then I have to give it 2 arguments. I have to give it the name of the input file. So MC example input, that's what we just made. And then I can give it whatever output file I like. It doesn't have to be a file that's already created. I can call this, you know, like, I don't know what, bottle. I don't care what, I got a bottle sitting in my office here. Bottle.out. I don't even have to put the dot out. I can call it whatever I want, but that's the name of the file it's going to write to. So there's 2 arguments you got to give it. I give it the name of my input file, the one I just edited, and then something that's going to be called the output file. And when I hit enter, you can see that it's going to get through these 20 steps fairly quickly. You don't want to do more than that unless you kind of submit it to the supercomputer. But this is going to take less than a minute to kind of test out. And it went through 10 equilibration steps and 20 production steps. Took about 0.2 minutes. And it wrote bottle.out. And I'm going to look at bottle.out and just show you a few things. It reminds you of kind of everything you gave it. So it tells me where I was, my temperature and density. It tells me what I called my input file, what I called my output file. We'll talk about movie files later. You don't necessarily need to worry about that. It says I used a random number seed that was specified in the file. And that's important because if I ever want to replicate this exact simulation, I can give it that number again. It tells me everything else that I put in here. How did I get this number? Energy tail correction. And pressure tail correction.
Isn't that from the integral from your cutout?
That's right. So that's what we talked about earlier today. I'm cutting off at 3. These are the energy and pressure long-range corrections to the energy and pressure that I get from assuming the radial distribution function goes to 1 at my cutoff. It gives you the initial positions that either you gave it in a file, that's what we did, or if it generated on an FCC lattice, it would give you those just so that you can have those in the future. I'm going to hit Control F to skip down a lot because there's 500 of these. Control F like is page down. And then it gives me every iteration. It gives me what the pressure is, what the average pressure is. So that those two numbers are the same because it started at 0, what the potential energy is. And then you can see I went through 10 equilibration iterations and then it reset and went through 20 production iterations. This is the type of data that I'm going to care about later if I kind of wanted to graph it and see how it's happening as a function of time. After it gets done with all the iterations, it writes the final positions to the file so that you could use those to start your simulation again. And then if it, oh, I didn't calculate my radial distribution function. I'll have to go back and fix that. It'll give you the radial distribution function. I'm giving it NAN because I gave it 25, but I never did 25 iterations. I'll show that in a second. I'm going to rerun that in just a second. And then after that, it gives the simulation averages. So here's the average pressure across the simulation, average energy, gives me heat capacity. We'll talk about that. And my move rate was 0.35. So 35% of the time it increased or did the steps. I'm going to rerun this real quick by changing the input file. And I'm going to change this number right here. I never calculated an RDF because I had this higher than the number of steps I did in equilibration of production. So I'm going to make this maybe, let's do 5. That'll give me a couple. When you hit up or down arrow, you can go through your previous commands. And so what I want you to just do is, practice with Linux a little bit and running this code. And we'll talk next time about how to compile it on Windows. Let me look at the bottle. So notice now I've got this radial distribution function. It gives me the bin value and it gives me what the radial distribution function is at that bin value. You'll notice I actually started at 0.8. It gives me the center of the bin value for graphing purposes. Right? I don't necessarily want, because the first bin goes between 0.8 and 0.83 or something like that, then I'm going to call the value of that right in the middle. So that's why it's in the middle there. But this will give me, you can kind of see if I graph this, I start at 0, below 8. It starts to increase that around 1, it's very high. And then it goes down below 1 at about 1.5. And then it starts going back up around 2. And then it goes back down around 2.5. And so you start to see these shells of atoms for your radial distribution function. Okay, we're up for time. I think graduate students we have some stuff in a minute. Next time we're going to keep going through some MC stuff. I'll tell you how to work on Windows if you want to work on Windows. In fact, send me an email if you want to learn to work on Windows rather than Supercomputer. But if anyone's had a problem with any of this stuff getting on the Supercomputer, let's make a appointment to meet so that I can get you set for this. Okay.
Side question. Control F is page down. What's up?
Control B, back. I don't know why it's called forward and back, I think is what it is.
Okay.
Control F is forward, Control B is back.
You would just want us to email you about setting up those appointments?
Yeah, just email me and we'll set up a time. If you want to go to the end of the file, it's capital E, so Shift E. We'll go to the, oh no. No, I don't know. What's going on here? Oh, Control Shift G. I don't know. I just have to think of my muscle memory. Shift G goes to the end of the file. And then if you do 1G, 1 Shift G, it goes to the top of the file. You can go to any line number with that. If I type 5 Shift G, it'll go to line 5. And then I can set the numbers. If I go into colon mode, then if I do set NU, set numbers, it'll give you the line numbers. And so there's all sorts, VI is such a huge, powerful editor. You'll notice that when I was hitting E or Shift E, it was going between each value, each word on the line. And so there's all sorts of commands that you can learn. Spend a little time doing that, and we'll talk more about this next time. Anything else? Okay, great. And we will see you next time then. If you have any questions about other tools you want to use, like if you want to use some other editors, then we can talk about that. If you're using Windows, another useful thing is called Notepad++. It's a better notepad than what's out there. And this allows you to kind of do a normal editor thing, right? I can copy, paste, I can write, I can do whatever. Notepad++ is something that you can use if you're using Windows. And it's free, you can download it. Okay. Thanks, everyone.